morning, ladies and gentlemen. Thank you very much for joining us today in our webinar to talk about Waterhammer Basics. It's great to see all of you in here, and we've got an awesome crowd. There's several of you in here joining in live, and it's good to see you all. Hope that everyone is having a very fine week, and we're going to have some fun today. And so we'll be talking about the basics with Waterhammer, and then we're going to dive into using AFT Impulse, and we're going to talk all about that. And so I wanted to start off with letting you all know that there are some amazing resources regarding webinar that you can find on waterhammer.com. And so if you go to waterhammer.com, this is where you can find some excellent resources, articles, a lot of good information like inherent versus installed valve characteristics and what that means. And so lots of information here. So if you've not been to waterhammer.com before, please be sure to go there and check it out, and you'll be able to learn a lot of good stuff. All right, so I was wanting to start off with a video today, but unfortunately I was having some technical difficulties with the usual microphone that I use, and I had to switch to a different microphone with a headset, and so I don't believe that the sound on the video is going to be able to play, so that would make it kind of challenging. Anyway, there are lots of videos on YouTube that you can find that demonstrate what Waterhammer is, and it can be a real big problem, and it can cause pipes to shake. It can burst pipes, collapse pipes. It can cause damage to pressure sensitive equipment. It can, damage the pump seals and bearings at the pump connections. Definitely something that you want to avoid. Some people might say, well, we don't have Waterhammer in our system, and that's just not true. Whenever you start up a pump, that causes Waterhammer. The question is, how bad does the Waterhammer get? And then, thankfully, there are ways that you can actually figure out how bad the Waterhammer gets. So what we're going to start off with talking about today is the instantaneous Waterhammer equation. And so this is also called the Joukowsky equation, and essentially, theoretically, the maximum theoretical surge pressure that you will see in an instantaneous event, let's say the classical valve closure example, where a valve slams shut, all that fluid comes to an instant halt, but the upstream fluid doesn't know that the downstream fluid has stopped flowing. And so there's going to be a massive buildup in pressure. So the instantaneous Waterhammer equation can help you determine how large that pressure surge is going to be, and it depends on what the liquid wave speed is. The wave speed of the fluid is dependent upon several parameters like the liquid acoustic velocity, the density and modulus of elasticity of the liquid, the pipe modulus of elasticity, wall thickness and Poisson ratio, and the pipe restraints. Is it anchored just at a couple ends or the upstream end, or is it anchored all throughout? All of these parameters will make an impact on what the wave speed is. And so all those parameters are taken into account in order to determine what the maximum theoretical pressure is. So we're going to do it's just a very simple equation. The pressure surge delta P, that's your instantaneous pressure surge. So you're going to have your density times the wave speed of the fluid times the change in velocity. The idea is that the change in velocity would happen very quickly. So if you are flowing at 10 feet per second and then it instantaneously stops, it's going to go from 10 feet per second to 0 in a millisecond. That is essentially as instantaneous as you can get. So if we take a very simple example with water, 62 pounds mass per cubic foot, and then a very nominal wave speed, 2,500 feet per second. That might be, maybe HDPE piping, perhaps. If it was steel piping, then your wave speeds are much higher, on the order of probably about 4,000 feet per second. Initial velocity, 10 feet per second, with an initial static pressure of 50 psia. So simply take these values and plug and chug them into the instantaneous Waterhammer equation, and then you're going to get a instantaneous pressure surge of 334 psi. Now, take that 334 psi, add it to the initial steady state pressure of 50, and your maximum theoretical pressure that you would see is 384 psia. And just a quick side note, this webinar is being recorded, and it'll be sent out later at the end of this recording. Okay. So that's the instantaneous Waterhammer equation. Now, if you want to do a actual Waterhammer analysis, you can't just stop with the instantaneous Waterhammer equation, because there is possibilities that you can see higher pressures than the maximum theoretical. And how is that? Well, if you are cavitating, when the static pressure in your piping drops to the vapor pressure, then you're going to have cavitation happening inside the pipes. And as cavitation happens, vapor volumes will begin to form, and they'll grow larger and larger. And then once they collapse on themselves, that's like balloons popping inside of the pipe. And that will typically cause pressures higher than the maximum theoretical pressure. So you can't just do the maximum theoretical and stop there. Another situation where you can have higher pressures is with line packing, usually with really long pipelines or higher viscosities especially. You'll see line packing where you have an increase in pressure over time after the initial event of a valve closure takes place. You can also have superposition of waves that are constructively building together to create much higher pressures. And so that's a situation where you can have pressures higher than the maximum theoretical. So if you want to do an actual Waterhammer analysis, you need to account for fundamental quantities. So we have the transient mass balance equation, and then we have the transient momentum balance equation. And so all this is stuff that you can easily find in the documentation for AFT Impulse, and you'll be able to find it all over the place on Google as well. And so the point is, you don't have to memorize these equations I'm trying to show you right now. Just remember that you need the transient mass balance equation and the transient momentum balance equation in order to do your calculations. Now, there's different ways that you can manipulate those transient mass momentum balance equations to solve for the transient behavior of what's happening. And one of the numerical methods that is really good at doing this is called the method of characteristics. So the method of characteristics combines the mass and momentum balance equations into a single equation, and you're going to integrate along what's called a characteristic line. Again, you don't have to memorize all this stuff. This is just what's going on behind the scenes if you're doing this type of analysis. After you have performed the integration, you have this final equation here. And the beautiful thing about this equation is, if you want to solve for the new pressure at a time step or the new mass flow rate, you can actually rearrange this equation where you can solve for these two parameters directly. So it does not require any iteration. It becomes an explicit equation. And so that's why it's much easier to be able to work with. So how do we do this in the method of characteristics? We create what's called a characteristic grid. So think of this as a pipeline here. So for a pipeline, we have x equals 0, that's at the inlet of the pipe. X equals L, that's at the outlet of the pipe. And then the middle point right here is going to be called x equals I. And so when you have this equation here for the transient mass and momentum balance, the flow rate, velocity, pressure, etc., is going to change all throughout the pipeline from one time step to another. And so all of these little red lines that I've drawn, all of these are computation stations. So if this valve right here slams shut immediately, the pressure, flow, and velocity that we see at this computation is not going to be the same at this particular time step that we see at this location right here, or this location right here. And so there's a concept called communication time, where when you have an instantaneous event, it's going to create a pressure wave, or a pressure wave and a velocity wave that are going to communicate themselves through the system. And so if I erase some of this madness here, when you slam that valve shut, it's going to create a high pressure wave where the pressure spikes, and then that wave is going to travel back and forth between the reservoir and the closed valve. And it's going to oscillate over time until the oscillations dampen out due to pipe friction. So because the flow rates, pressures, and velocities are not the same at each individual computation station, this is why we have to use these numerical methods to calculate what the parameters are at each computational point. So remember that computation stations are these computational points where we are solving this transient maximum balance equation. So at time 0, this is the initial steady state conditions. So before the valve has even started to close, we're operating at a steady state. Then we can use the simple Bernoulli equation to calculate what the steady state flow is in the pipe, which is going to be constant, the steady state velocity, and the pressure profile through the pipe. It's just going to be a pressure drop. So all of that is calculated with the Bernoulli equation at time 0. Now, here the valve slams shut, and we want to calculate what is happening at the first time step at every computational point throughout the pipeline. And so where I'm drawing these little red dots, again, those are the computational stations along the pipeline, where we have the inlet right here. This is the inlet at the first time step. This is the outlet at the first time step. And this is station I at the first time step. We're going to call this point P, okay? So in the middle of the pipe right here, if you want to be able to calculate after a instantaneous valve closure event, what is going to be the new pressure and flow rate at this particular time step? This is why the method of characteristics is really useful, is because you can directly solve this equation for the new pressure and the new mass flow rate based upon the previous time steps, immediate upstream pressure and values, and the immediate downstream computation station values. And so that way you can simply draw a line from these values to these values, and you can calculate that directly. So this is called a characteristic line. the positive characteristic, because you're going from a x minus 1 to a higher station number value. And then here you've got a negative characteristic line. And so this equation can be written for both of those characteristic lines, either from point A to point P or from point B to point P. So we're going to have a characteristic line for every time step at every computation station. And so it would look something like this. So that will give you the values for pressure, flow rate, velocity, everything that you want to know at the first time step. Once you've solved for everything at the first time step, then we go from the first time step to the second time step. Same process. All we're doing is we're just creating this characteristic grid, and this characteristic grid in blue is going to calculate the transient pressures, flow rates, velocities at the second time step, which is going to be based upon the immediate upstream or downstream parameters of the previous time step. And then we just keep going, so on and so forth. And then we have right here the third time step, those characteristic lines. And so that's how we would be able to move forward in time, as well as determining what's happening in space. Now, you can do this fairly easily by plugging in these equations into a spreadsheet to solve this situation. And this is what that would look like. So here I have a spreadsheet where I'm doing exactly this calculation process. So this example is for a 2,000 foot long pipe. Give me 1 second. All right, it's for a 2,000 foot long pipe. Station 0 is at the inlet of the pipe, and we're going to use 10 computational points inside the pipe, and these are called stations. The last station, station 10, is at the outlet of the pipe, 2,000 feet. And so if we're doing 10 stations in 10 computational stations in a 2,000 foot long pipe, then the distance between one station to the next is going to be 200 feet. So as you can see right here, station 7 is at 1,400 feet. Station 8 is at 1,600 feet. So we're creating this characteristic grid in Excel, and we are taking our pressure and our mass flow rate, and then we are using those values to do all the math behind the scenes to calculate the characteristic plus line and the characteristic minus line. These are impedance values. Not going to talk much about that, but ultimately what I'm trying to demonstrate here is going down is our time step. Okay, so our time step is very small. It's about 51 milliseconds. And so with all of these equations being solved numerically, when you plug in the equations for all the cells, everything just becomes automatically calculated. And again, there's no iteration going on. All this stuff is happening directly based upon the immediate upstream and downstream stations at the previous time step. So if I was to click on any of these cells right here for the characteristic plus line, you can see that it's not requiring any iteration. Now, what do we care about? We care about what the pressure is in the pipeline and how large it gets. So, namely at the valve. The valve is going to be where you're going to see the highest pressure surge. Okay, usually. So what we're doing now is we are plotting the transient pressure at the valve inlet, which is simply station 10. So station 10 represents the valve inlet, and this is just plotting, it's copying the pressure versus time at that computation station, and this is a plot of those values. So if we look at this here, we can see that when that pressure spikes, when the valve slams shut, the pressure spikes to about 660 psia, about. Well, 667. And so that's how high the pressure gets. Now we can use the Joukowsky equation to see if the instantaneous pressure equation matches. Now, something that I want to point out here is when the pressure stays at a high point for a little while, the reason why the pressure stays up at this point is because the high pressure wave that's being created is going to communicate itself upstream to the reservoir. So that's where the pipe has a high pressure. When the wave communicates itself back, we're then going to have a negative wave reflection. Now, that doesn't necessarily mean negative by value. It means basically that we're having a negative reflection. So, here is our positive wave, and then here's the negative wave. So I'm not meaning exactly negative pressure. It's just the negative wave reflection, okay? Now, we do actually see negative absolute pressures. What in the world is going on that we see negative absolute pressures? Well, this is something that will happen mathematically. What this indicates is that there is cavitation going on during that time frame. And so how far negative that pressure goes can give you an idea of about how large that volume is going to get. So this is one of the traditional methods of evaluating cavitation, where if it goes negative 200 psi, then you could expect to see a 200 psi pressure spike when the vapor bubble collapses, and we have the next pressure spike right here. So this is what it would look like if you were to program the transient maximum momentum balance equations into the method of characteristics with a spreadsheet. Not too difficult to do. Now, I've talked about computation stations. They are mathematical points along the pipe where we are doing a calculation. So it is an actual distance along the pipe. So if this is a 60-foot long pipe and each station is 10 feet, then this is 10 feet, 20 feet, 30 feet, so on and so forth. Now we also have the terminology called sections. The section is the chunk of fluid between two computation stations. So this is the first section, second section, third section, fourth section, etc. The pipe sections have a volume associated with them. So remember that. When you're doing this calculation with the method of characteristics, the sections, the section lengths and the station distances, they have to be the same. We cannot have fractional sections, like 2.5 sections in a pipe. We need to make sure that all of the sections are equivalent, and I'll talk about that here in a little bit. So this is just giving you an idea of, if you were using AFT Impulse, how things are numbered. So in this particular case, we have pipe 1. This is pipe 1 station 0, pipe 1 station 1, pipe 1 station 2. And then we have pipe 2 station 0, that's the inlet, pipe 2 station 1, so on and so forth. All right. The communication time, again, is a concept that I talked about where it's the amount of time it takes for a wave to communicate itself down a pipe to let things know that something has changed, and then for that wave to propagate back. And we're going to be able to see that very clearly with animations. All right, I want to talk a little bit more about pipe sectioning here and the time steps. So when we consider that characteristic grid, the time step is not just chosen to be whatever you want. You can't just say, I want my time step to be 20 milliseconds. That's not how it works. The way that we determine the time step is going to be based upon the wave speed of the pipe and the pipe length. Give me 1 second here. Excuse me. Okay, so the maximum time step is going to be based upon the shortest pipe in your system. The reason why is because these wave speeds are very fast, several thousand feet per second. And we want to make sure that we have enough time step resolution that can capture the very fast transient behavior. So we're going to look at the shortest time step, we're going to look at the shortest pipe in the system and calculate the largest time step that you can possibly have. So the time step is equal to the shortest pipe in the model, the length divided by its wave speed. This is going to assume that we're only putting one section, simply an inlet and outlet. There's going to be no intermediate pipe stations in that controlling shortest pipe. One section. Once the time step is determined, then the amount of sections for all the rest of the pipes can be determined by this equation here. So let's consider this situation where you have a pipe where we've got a 10-foot pipe and then a pressure gauge and then a 10,000 foot long pipe. In this system, this particular pipe is obviously the shortest pipe in the pipeline. So what we do is we take that pipe and we use this equation to calculate what the largest time step can be based upon putting one section in the controlling pipe. So let's say that this particular 10-foot long pipe has a wave speed of 4,000 feet per second. So we're going to take 10 feet divided by 4,000. Our time step is going to be 2.5 milliseconds. Okay. If we make our time step larger than this value, then we might miss pressure spikes that are happening during that time frame. Like let's say that we make it 0.1 seconds for our time step. Well, with a 4,000 foot per second wave speed, we could be missing a lot that's happening in that time frame. So this is where we need to make sure that we have a small enough time step to capture all the transient behavior. Now that we know the time step is 2.5 milliseconds, we can then calculate how many sections are going to be in the 10,000 foot long pipe using this equation right here. So let's take 10,000 feet divided by, let's pretend it's the same wave speed, 4,000 feet times 0.0025. So, I mean, simple math makes this real easy. You know, 1,000 computation stations in the 10,000 foot long pipe. Now, what happens if we double the amount of stations or sections in the short pipe? So instead of doing one 10-foot long section, we're going to do 2 5-foot sections. Well, then that's going to double the amount of sections that we have in the pipe. That's going to increase the runtime by a factor of 4. And so the reason why I spent a lot of time on this is because pipe sectioning is your biggest impact on runtime. Simply stated, the more sections and stations that you have, the longer that your runtime is going to be. So if I made this 1 foot, if this was a 1 foot long pipe and a 10,000 foot long pipe, then we're going to have 10,000 stations in that long pipe. And that's going to lead to a really long runtime. Now, the question is, when we're dealing with sectioning our pipes and we have, let's say, the pipe comes out 8 feet and then it has a couple of elbows and then, we've got 1 foot here and 1 foot here, and then we have our pressure gauge. You might be tempted to model this type of situation explicitly, where if this is 8 feet long right here, the shortest pipe in your model would be these stupid little 1 foot long short pipes. And the question is that necessary to be able to have an accurate model? And I'm going to say no, absolutely not. You do not have to have that level of resolution or that level of accuracy to maintain an accurate model. Instead, what you could do is you can take those 2 elbows and you can lump them in as additional fittings into your pipe and still keep it as a 10-foot pipe. Why is it that you can, or sometimes let's say that somebody made this be 1 foot? Well, look at your shortest pipe in your model and your longest pipe. If it's 1 to 10,000, then that's a pretty big difference. Give me 1 second here. So if you have a really big difference in pipe lengths like that, then there are multiple practices that you can do, either combining pipes or simply making your really short pipes a little bit longer. We could even make this pipe be 100 feet. If this is 10,000 feet and we make this 100, that's okay, and that is not going to impact the results very much. Why? Well, A, if you are considering the Darcy-Weisbach equation, the FL over D times 1/2 rho V squared and all that good stuff, the thing to remember is that your pressure drop in the pipe is proportional to length divided by diameter to the 5th power. So as long as your diameters are correct, you can make your pipe length a little bit longer arbitrarily, and it's not going to make a significant impact on your pressure drop. The other reason is due to the communication time. So if I go back a slide and we look at the communication time in here, that's the amount of time it takes for a pipe or for a wave to travel through a pipe. So let's say that we have a 10-foot pipe. 2 times 10 divided by a wave speed of, let's say, 4,000 feet per second is 5 milliseconds. That's for a 10-foot pipe. Let's say that we make that 10-foot pipe 100 feet. 2 times 100 divided by 4,000 is 50 milliseconds. So the difference in amount of time that it takes for a wave to travel being 5 milliseconds versus 50 milliseconds is hardly anything. You'd be very hard pressed to actually find any pressure measurement devices that have a sensitivity good enough to be able to capture that difference. So that's the other reason why you can make your short pipes arbitrarily longer. Okay, so again, more sections and more stations equals longer run times. This is the wave speed equation. You can easily find this in the AFT Impulse help documentation. I'm not going to spend much time on it, but what I do want to point out is, again, we cannot have fractional pipe sections in a pipe. So what we need to do is we need to round off the computing sections so that each pipe has a whole number of sections in the pipe. This introduces error into the sectioning. What we do, recognizing that wave speed is the least certain parameter, that's key. We're going to modify the wave speed in order to achieve a whole number of sections in each pipe. And the traditional approach is you can allow up to plus or minus 15% of wave speed difference in order to get a whole number of pipes. This plus or minus 15%, that does not mean that you have plus or minus 15% error in your results. That is not what that is saying. It's simply saying that if your wave speed is 4,000 feet per second, and we need to increase it by 15% in order to get a whole number of pipes, it's going to be 4,000 to 4,600 feet per second. And this is typically not going to make a significant impact on results. So as you are first starting out, when you are doing your initial analysis, start with a larger number, start with a larger size of pipe sections, one section in your controlling pipe. And then let the initial error in wave speed be 15% or even higher, 25%. That's okay to start with, because you can get a handle of what's going on in the results of your model, and then you'll be dealing with much shorter run times. You might have to do a lot of troubleshooting. Now, after you start to get a handle of your results and you understand what's going on in your system, then you can start putting in more and more sections and stations dealing with longer run times, and that way you can refine the results in your model. All right, we're going to go ahead and do an example now. We're going to compare this. This is actually the same calculation as the Excel spreadsheet that I just showed you. So we're going to do the same calculation from Excel in AFT Impulse, and then we're going to compare this to the instantaneous Waterhammer equation. So if you remember, we actually saw a pressure of very close to 663 psi. It was actually 667 psi from Excel. That's how large the pressure surge got. That very closely matches the instantaneous Waterhammer equation. Well, how does it match when we're building this in Impulse? I want to note that Impulse does not have any Joukowsky equation built into it. It's not solving Joukowsky. It is solving traditional mass and momentum balance equations with the method of characteristics. All right. So here's AFT Impulse. We're going to build this model real quick. Here's how you do this. It all starts with the red status light in the bottom right corner. That will lead you down the yellow brick road of what you need to do to build and define a model. So if I click on that red status light, it's going to pull up the analysis setup window, and the next piece of the yellow brick road is to follow the red exclamation points. The red exclamation points indicate that you have to do something in those items. So here we have several groups. If I was to collapse all the groups, we've got modules. If I was to collapse this, we've got our fluid groups, our pipes group, etc. So let's just focus on the red exclamation points. Your red exclamation points indicates required input. So the required input that you need for a fluid is simply density, viscosity, and bulk modulus of elasticity of the fluid. Now, vapor pressure is optional. I highly recommend that you specify a vapor pressure. That way Impulse can do the cavitation calculations. All right, so this example, we're going to use water. So I'm going to use AFT standard water. I'm just going to add it to the list, follow the exclamation point. Our temperature is going to be 65 degrees. Bam, there's our fluid properties. Once you complete this step, you'll then get a green circle with the check mark. That means that item is done. So I'm all done with the fluid. I don't need to do anything else. All this other stuff that has a green circle with check marks, those are things that have already been completed for you. You don't have to do anything in there unless you want to change something in there. All right, so if I click OK, the next thing I need to do is I have to build my model. So I'm going to have my reservoir, I'm going to have my valve, and my pipe. Voila. Now I like my font size to be a little bit larger, so I'm going to make that bigger. Let's make it 20 and 20. There we go. All right. Okay, so now that my piping system is built, if I go back into the analysis setup window, it's going to automatically go to the next section that needs to be defined. It's telling me that my pipes and my junctions are missing input information. If I click on these, it'll actually tell me exactly what input is missing. So this is a really good guide to where if you have a model with 500 pipes and junctions and you're missing a diameter somewhere, really, this is a really quick and easy way to help you find that. Another couple of ways is if you click on the light bulb right here, it's going to highlight any pipe or junction in red, meaning that those items are not fully completed. You can also click on the button next to it. This pulls up a panel of that same information, which pipes and which junctions are missing input information, and it'll tell you what input is missing when you click on them. Define stuff just by double clicking on it. So I'm going to start with my upstream supply reservoir. The next piece of the yellow brick road is your light blue highlighting. Wherever you see this light blue highlighting, that indicates required input. So this is going to have a liquid surface elevation of 500 feet. I'm not going to do pipe depth, I'm going to do pipe elevation, and this is going to be 470 feet. That puts 30 feet of head above the pipe connection. Click OK. Once that's done, that label turns black. That means that that junction is now completed. I can go into my valve here. Same thing, follow the light blue highlighting. This is going to be at an elevation of 0 feet. My initial fully open CV value is 530. So 530, I'm going to go to the transient tab because I have to define a transient to cause Waterhammer to happen. So I'm going to slam the valve shut very quickly. 500, it's going to go from a CV of 530 to 0 in 1 millisecond. And that's how fast I'm going to close it. Now, this is not realistic. This is a 20-inch diameter pipeline. Closing a valve in 1 millisecond for a 20-inch diameter pipeline is very unrealistic, but it's to illustrate Waterhammer, so that's what we're dealing with. I forgot to do one more thing. We have to specify this as an exit valve. That means that there's no downstream piping. This is discharging straight into the atmosphere. So that's where we choose exit valve and then define an exit pressure. This is simply the pressure of the ambient conditions you are discharging into. So 0 PSIG. There we go. Now the T means that there's a transient defined there, so there's a transient. And then the pipe. So this pipe right here has a lot of required input, but if we choose from one of our pre-built pipe material libraries, then I can select things much more easily by nominal size and schedule. So this is going to be 20-inch, standard schedule 20, and here my wave speed is going to be 39 and 80 feet per second. And it's going to be 2,000 feet long. All right, click OK. So now if I go back into my analysis setup window, we can now see that the pipes and junctions section is done. The next thing to do is to section the pipes. Now, there's only one pipe in the model and it's 2,000 feet long. So I don't want to do just one section in this case. I'm going to do much finer resolution. I'm going to start with, let's go ahead and do 10 sections. So when you put in 10 sections, this is going to look up to putting 10 sections in that pipe. So here, if I click on row 1, this is going to tell me how much the waves, this is going to give me the detailed results of the sectioning for all the pipes. Well, this is one pipe, so it's not very exciting. But it's going to tell me the initial wave speed, how many ideal sections there are. This might be fractional. We can't have that. We have to have a whole number. And then this is going to tell us how much we have to change the wave speed in order to get a whole number of sections. And then this is what the modified wave speed is going to be. Now, for a 2,000 foot long pipe with one section, no change in wave speed is required. If I did something like 3, then that's going to give me something a little bit different. I'm going to do 10. So I'm putting 10 sections in that controlling pipe, and that step is now complete. Now, output pipe stations, this is really important because if you remember from that characteristic grid, I have all of those intermediate computation stations that are in the pipe, and I care about what's happening in there. So what you want to make sure that you do is save all of the intermediate stations for all of your pipes. Here's how you can do this very easily. First, click on the button that says All. When you click on the button that says All, it will select all pipes. And then you can click on this button where it says Set all pipes to be all stations. So now I've got 20 computation stations in the pipe because I did 20 sections. This is going to save the output results for all the interior computation stations. And that's really, really important. And I'll show you why here in a little bit. All right, so we've got output pipe stations. The last thing here is simulation mode and duration. You can do just a steady state calculation if you want, but here we're doing transient. We're going to see what happens in 10 seconds. Now, initially, I'm going to turn cavitation off to see how this matches the Excel spreadsheet. So I'm turning off cavitation initially. Now I have a green status light. Everything is done. I can now run my model and get results. Let's save it first. I'm going to call this Ben's valve closure. All right, let's run it. Okay. So first things first, what is the maximum pressure? Well, here, 683.6 PSI. Well, that is a little bit higher than 663. It's 20 PSI higher, than what the instantaneous Waterhammer equation predicted. Now, the thing is, if we paid close attention, this is using a wave speed of 3,876 feet per second. The wave speed in my pipe here is 3,980. So we do have a higher wave speed, and I think that that's because the fluid properties are slightly different than the example. So if we look at the density, we've got 62.3, and we've got an initial steady state velocity of 8.4. Our fluid properties here, density is 63.3. Our initial steady state velocity is 8.44. It really comes down to rounding and numerics that's causing those differences. So not a big change. And that's the thing, is with Waterhammer, there isn't really a boxed in answer that you're going to find. Is the result supposed to be 663 psi, or is it supposed to be 667 psi, or is it supposed to be 683 psi? Well, that's a bit of the unknown and a bit of the black art that comes with Waterhammer modeling. You have to look at the trends to see, are these at least consistent and of similar magnitude? We can get a better handle of this if we do a plot of the pressure at the outlet of the pipe. So if I plot the pressure at the outlet of the pipe, this looks the same as what we were seeing with the spreadsheet here. So this shape and trend is consistent. So this is accurate with what's going on. It just has some very slightly different numbers somewhere where we see that pressure. So if we look at this pressure here, we see 676 psi, a little bit higher. This is where it's 683. This is the line packing. We got a 2,000 foot long pipe. That pressure is going to build up a little bit more due to the slight compressibility of the liquids. Now, let's do what's called a animation of a profile. So if I click on the profile tab, I want to see what's happening with the pressure in the entire pipeline at every time step. This is where we're going to use the animation option. So this is where I said it's necessary, and I highly recommend that you save all of your stations initially and deal with a slightly longer runtime. The reason why is because it gives you the ability to use the output option. So here I'm going to plot my maximum and minimum pressure with the output animation. And when I go to play this, things happen very, very quickly. If I am using the output option, I can pause the animation and I can back up time steps. I can go backwards in time, and then I can move forward one time step at a time to see exactly what's happening. This is extremely helpful for understanding Waterhammer with what's going on in your system. If you did not save all stations right here, if you kept this as using inlet and outlet only, you would not be able to use output. You would only be able to use solver. If you're using the solver option, you would not be able, you could pause, but you would not be able to back up time steps. So this is why I suggest to always use all stations, deal with the longer run time up front, and then that way you can get full functionality with the output option, so you can pause and back up time steps. So this is the Waterhammer sequence. I'm going to add the velocity of the fluid as well, and I'm going to take off the maximum and minimum pressures. So when I go one time step at a time, boom, valve slams shut. That causes our spike in pressure. We can see how the velocity instantaneously drops to 0. And then as I move forward time steps, we can see how this wave, we've got a pressure wave that is high. We've got a high pressure wave passing back to the upstream reservoir, which is the reflecting point. And then we also have a velocity wave where the velocity is essentially trying to tell the pipeline, hey, we all need to come to a stop because we can't flow anymore. So as I keep going forward, that pressure and velocity wave is going to reflect up to the reflecting point, which is the reservoir. That reservoir is a fixed pressure. So the pressure of the pipe is not going to change the pressure of the reservoir. So it's going to reflect off the reservoir. And now we're going to have a little bit of reverse flow. So we can see how the velocity drops negative. This is where the flow starts reversing into the reservoir a little bit. And we can see how the pressure drops to essentially what it was in the initial steady state. So we can see this wave reflect off the reservoir back to the closed valve. Now, once it hits the closed valve, the pressure was high the whole time for that initial wave cycle, down and back. Now that it reflects off the closed valve again, this is where we're going to see that negative reflection. So here we have our negative reflection. We can see it's negative 200 psi, not necessarily negative number, it's just a reflected sign essentially. And so now we have a low pressure reflection. And so low pressures are just as bad as high pressures. With low pressures, you could be cavitating, very bad things, causing pipes to collapse. So it's not just high pressures that you need to avoid, it's also low pressures. And this gets really low. Look how low that gets as we move all the way down move all the way back up the pipeline. This all, with it being negative absolute pressure, this means it's cavitating. And then this is simply going to continue to oscillate. And it oscillates until essentially friction causes it to dampen itself out. Now, that is with ignoring cavitation. Since we now know that we have cavitation because we've seen negative absolute pressures, let's turn on cavitation again and let's see what our maximum pressures are. So if I rerun my model, oh my, look at that. I've got 955 psi as my maximum pressure. Whoo, wowza. Well, let's take a look at the pressure at the valve again. Here's another way that you can create a graph. You can right-click on a junction or a pipe, and you can create a transient junction either for the junction, or you can do a transient graph for the pipe. So let's look at the static pressure at the valve. So here, initially, this matches what we saw before when that valve slammed shut for the first time, 680 or so psi. And then when that negative wave reflection hits, boom, it drops to vapor pressure. So now let's go ahead and add the vapor pressure to see what's happening. vapor volume percent. All right. So when that pressure drops to vapor pressure, we can see a vapor bubble start to form. And that vapor volume gets to be about 1.25% of the section volume. So a 200-foot long section of pipe, 1% of that is pretty small. Just very small foot or whatever it is. Now that vapor volume decreases. Once that vapor volume hits 0, it pops, and we're going to see a pressure spike. And the pressure spikes up to about over 200 psi. But as we cavitate further and further with more and more vapor volumes, eventually we see a much bigger pressure spike here, and then another one that's even bigger later on. Are those real? Well, this is where you have to take a much more detailed look at the cavitation. A few things you can do. You can try doing more sections. So instead of 20, let's do 40 sections. And am I going to see the same magnitude, 955 psi of pressure when that spikes? Well, now we're at about 1,073. That's still relatively close in terms of magnitude that we saw before. So if I do that same plot of pressure and vapor volume, the trend looks very similar. So it is certainly different numerically. I mean, we do see higher volumes, obviously, because we made our section volumes shorter, smaller, but we do see a high pressure spike here and here, about the same timing and about the same magnitude as before. The next thing to do would be to change cavitation models. So the discrete vapor cavity model is robust. It solves a little bit easier, but it causes a lot more anomalous pressure spikes that may not be real. It's going to put a lot more noise in there for sure. The discrete gas cavity model does a lot better. So if I switch to using the gas cavity model, we'll take a look at, and that comes back down to 830. Well, if we look at those same two plots at the valve inlet, we're seeing less noise, but similar behavior. So we still see high pressure spikes at about 800 psi. So now that we've changed our sectioning, we've used a better cavitation model, and we're seeing similar results and similar trends, those might be realistic spikes. There's another thing that we can do. We can change the friction model to a more advanced friction model. This captures a unsteady shear stress term for the friction factors. So this gives a little bit more smoothing out of what's going on. I'm just going to go straight to the graph. And I'm going to plot the same thing, vapor volume and pressure. And we see essentially the same thing. Now, it does drop a little bit later on, but this first spike is still above 800. So this guy and maybe this guy, those might be fairly realistic spikes. So yes, you need to design to handle that high pressure. Really? No. Well, yes and no. Ultimately, your goal should be not just to evaluate the cavitation and live with it. Your goal should be to eliminate the cavitation. Get rid of it. And so right now, this is still based upon a closure time of 1 millisecond. That's a very fast valve closure that's going to cause very large pressure spikes. What if we close it in 1 second instead? How much does this help to eliminate cavitation? Well, let's see. So if I go to my output window to check, I can see 680 PSI. That's better than 800. If I do that same plot for pressure and vapor volume, well, we still see some bigger spikes right here and a little bit of noise, and we see a very tiny amount of vapor volume. So you could probably live with that, but let's see if we can get rid of it altogether. So let's try 2 seconds. So if I change this to 2 seconds and rerun it here, wow, 404 PSI, much, much better. So we do 404 PSI, and I take a look at those same plots. It looks big with the vapor volume, but look at the scale, 10 to the negative sixth. So this is virtually zero. So by closing the valve in 2 seconds instead of 1 millisecond, that completely eliminates the cavitation, and we can rest assured that this is a much more realistic prediction of pressures, because when you're cavitating, it's always going to be questionable whether those results are realistic or not. But when you have eliminated cavitation, you can rely much better on those results. Now let's do one more thing. Let's say that we have a pipe split that occurs, let's say 700 feet down the line, or actually let's put it closer to the end. Let's say 1700. So at 1700 feet, I've got this pipe split, and I'm going to put another flow path here. I'm going to take this guy, and we're going to make this, let's make it 200 feet. Actually, let's make it 150. And let's change the diameter to 10 inch, just to have a little bit of fun. We'll go ahead and close this guy as well in the same way. So we've got these two valves. We're going to close them both in 2 seconds. This pipe here is still 20 inches in diameter and 300 feet long. And we're going to take these two valves. Let's see, call this valve names. And then I'm going to add the valve name as a parameter. Call this guy valve 2. And we're going to call this guy valve 1. Now we've got multiple flow paths. This is the last thing I'm going to do today. So hang in there with me just a couple more minutes. I'm going to select these two pipes in this continuous flow path. I'm going to create a group. So I go to edit, groups, create. I'm going to call this path, or I'm going to call it tank to valve 1. And then I'm going to deselect that pipe and select the other one. I'm going to create a second group, tank to valve 2. Now we do have some new lengths in here, so we do have to go in and reset our sectioning. Now it's no longer just a 2,000 foot long pipe. We've got 150 feet as our shortest pipe in the model. So this is where we're going to be a little bit more strategic. Let's put, I'm going to put 10 sections in that controlling pipe. this shouldn't impact the run, 28 seconds, so that's not massive. Make sure all stations are saved. We're still going to keep cavitation and all that stuff turned on just in case. And this is where we need to really do an analysis. This is where a spreadsheet would be much, much more difficult to do. The moment that you've got a flow split, it's going to be a lot harder to do this by hand. Now, this does not give you the whole story. This is where it's really important to use your animations. So the reason why I created those two groups was because I want to plot multiple paths using groups, and I'm going to plot both of those groups together. Let's look at pressure, and let's look at flow. All right. So when we look at our maximum minimum pressures, that's why we got so many lines down there. I'm going to take off the maximum minimum values. We're just going to look at the animations. All right. Slow it down a little bit and play. Okay, so I do need to speed it up a little bit here. Okay, so both of the valves are closing within 2 seconds. You can see how the pressure in the line, the whole pipeline is increasing, and you can see how the flow is dropping at the same time. And so as we play this and move forward, boom, valves slam shut. Now, the reason why I'm showing you this is because you're going to see some interesting oscillations between this portion of the system and the upstream portion, and how that's going to cause some potentially constructive or destructive wave interference patterns. So this is another situation where you might have larger pressures. We are cavitating. You can have larger pressure spikes due to the superimposition of waves up and down the pipeline. And so here, this is just showing how you can have some interesting behavior and how it can potentially cause issues. So the moral of the story of why I did that pipe split is to not just neglect the short legs. You might think, oh, well, this pipe is only 10-inch diameter. I really care about what's going on at this valve. I don't care about what's happening in this pipe. Well, the problem is that you have stuff that's going on in this pipe, which is going to interact with things happening in this pipe. And that's going to change the behavior of what's going on in this pipe than if this was not in your system. So with Waterhammer simulation modeling, you cannot just ignore other pieces of your system. You have to include all of the branch points and your dead legs. Let's say if this was not a valve, but instead it was a dead end. If this was a dead end and there was no flow in that pipe, that would still impact the wave behavior that's going on in this pipe. Because if this is a dead end, it is now a reflecting point. So if that was your situation where you had a dead end right here, you're going to still see pressure oscillations in this pipe moving back and forth. So you cannot just neglect your dead legs, especially if they have a decent amount of length to it. You might start cavitating in those dead legs, and that could be a problem as well. So anyway, that is a very small introduction to Waterhammer and how you can simulate it using Impulse, and hopefully the a little bit of the theory and the background of the instantaneous Waterhammer equation and how the method of characteristics are solving things helps to make what Impulse is doing make more sense. And so it's a black art, and it can oftentimes be not so straightforward. Did you know that AFT has a sister company called Purple Mountain Technology Group, which we do consulting services? And so if you go to pmtechgroup.com, I am the project manager and senior consulting engineer at PMTG. And if you need some extra assistance with evaluating your Waterhammer or anything hydraulically related, contact us and we'll be able to help you. And I'm going to go ahead and put my email up here, Ben Keyser at PM Tech Group. Let's try it again. It's too big. We'll make it. All right. Ben Keyser at pmtechgroup.com. So if you email me there, Ben Keyser at pmtechgroup.com, then I'd be happy to help you with any additional assistance that you need with your hydraulic modeling, your Waterhammer modeling, pipe sizing, pump sizing, whatever it is. Give me a shout out, and I'll be glad to help. Thank you all very much for listening in today, and I hope that you enjoyed the show. Take care and have a wonderful rest of your week.